what is electrical conductivity, what is the expression for the electrical conductivity. So yesterday we derived the expression for the electrical conductivity. This was the expression, sigma is equal to n E square tau upon m, where n is the concentration of free electrons, E is the electronic charge, and tau is the relaxation time. Yeah, tau is the relaxation time, and m is the mass of the electron. And I also told you that the difference in the conductivities of the metals is only due to the variation in the concentration of the free electrons, because you can see from this expression that sigma is directly proportional to n, which means that the conductivity is directly proportional to the concentration of the free electrons. So therefore, any metal having larger number of free electrons will have more conductivity as compared to the metal which is having lesser number of free electrons. Okay, so this was the expression for the conductivity. Then I told you that we are also going to derive the expression for the drift velocity, or the expression for the average velocity of the electrons. Okay, so let us suppose that under the influence of an electric field Ex, the electrons have a certain drift velocity uh, Vx, x is in subscript, Vx0, at any time instant when when there is no field, at any time instant, let's say t is equal to 0, right? However, after time t, the velocity is denoted by Vx. Okay, so if I talk about the relation between Vxt and Vx0, the relation will be, because the velocity is decreasing when the electrons are colliding with the positive ion present in the lattice, right? So there will be an exponential relation between Vx and Vx0, and the relation will be Vxt is equal to Vx0 exponential minus t upon tau, right? So you can see that the velocity of the electrons roaming around the system, when they make a collision with the positive ions present in the lattice, there is an exponential decay of the velocity of the electrons, right? So from this equation, this was equation number 4. So you can easily derive this equation. This is just a mathematics behind this relation. See, I will let you know how to derive this equation. Sorry, this was equation number 8. Okay, so if you see the equation number this one, equation number 4, right? If you see this equation, if we can take this equation and we can just derive that exponential relation, right? So this was the variation of velocity with respect to time is equal to the average velocity of the electrons divided by relaxation time. So if you take this relation, by using this relation we can reach to equation number 8. So the equation was from equation number 4, dvx upon dt is equal to minus vx upon tau. If you integrate this equation on both sides, you'll get integration of differentiation of vx By the term Vx means Vxt. Okay, Vx divided by this Vx we can take on this side, and this is Vx which is further equal to minus dt divided by tau. Okay, so this is, what is this? The integration of this left hand side will be natural log Vx, which is equal to minus t upon tau, because the integration of dt is t. So this is minus t upon tau plus constant of integration, right? And this constant of integration is how do you determine this constant of integration? See, at t is equal to 0, at t is equal to 0, c will be equal to, when you put t is equal to 0 here, then c is equal to natural log v 0. Sorry, v at t is equal to 0. Okay, so it means that c is equal to this one. If you substitute the value of c is equal to this one here in this equation, then this will be natural log vx, and this is at time t is equal to minus t upon tau plus natural log v at time t is equal to 0. If you take this term to this side, then this is natural log vxt, this is minus natural log v0. So you can write it as natural log, this can be written in terms of division, so this will be vxt divided by vx at 0, and this is further equal to minus t upon tau. It means that if you take exponential on both sides of this relation, then natural log is cancelled out by exponential. So this will become vxt divided by vx at t is equal to 0. This is equal to exponential minus t upon tau. If you take this division term on right hand side, then this will become vxt is equal to vx0 exponential minus t upon tau. So this is our equation number 8. This is what we wanted to find out. Okay, so this is the drift velocity of the electrons at any time instant t, right? So and vxt is the drift velocity of the electrons under the influence of the electric field when the electric field is applied at any instant time, at any instant of time t. Vx naught is the velocity of the electrons when the field is switched off, when there is no field at time t is equal to 0, right? Tau is the relaxation time. So this is the relation between the velocity of the electrons. Yes, is it clear? Any doubt here, students? Yes, students, any doubt in this?
No, ma'am.
Okay, great. So next article is very important article, the Boltzman transport equation. Boltzman transport equation. See students, the transport properties of the materials or the transport properties of the metals is totally dependent upon the distribution of the electrons within the bulk of the material, right? And if by using some method if we are able to locate the electrons within the bulk of the material, then we would be able to define the transport properties of the materials. We would be able to define the conductivities of the materials, right? Because the distribution of the electrons is very random in the absence of any electric field, in the absence of any external force. So if we are able to find out the position of the electrons within the bulk of the metal, then we can define many transport properties of those metals, right? So in order to describe the transport properties of an electron gas, we need to know the distribution function of the electrons. The function will tell us how the electrons are distributed in momentum space or k space, right? From this information, all the transport properties can be evaluated. So while discussing the transport properties, while discussing the band theory of solids in your previous course CMP1, you might have learned about the EK diagrams, energy momentum diagrams. You might have learned about the momentum space. You might have learned about the position space, about the uncertainty principle, right? So these terms you have used in your previous course, which is CMP condensed matter physics 1, right? So while going for this particular article, I will assume that you are aware of those things, right? Okay, so at equilibrium, you might have studied this free electron theory, and using free electron theory, you have also studied the distribution of the electrons, how to determine the distribution of the electrons within the metals, right? So, but that distribution was at equilibrium. Okay, so at equilibrium, the distribution function is simply given by the Fermi-Dirac function. Fermi-Dirac function. आप लोगों ने पढ़ा है Fermi-Dirac function in free electron theory. At equilibrium, the distribution of the electrons is defined by the Fermi-Dirac function, and Fermi-Dirac function is given by Fe is equal to 1 upon exponential E minus EF divided by K B T. B is in a subscript plus 1. Okay. So in this expression, you might be knowing E is the energy of the electron at that particular moment, right? And EF is the Fermi level, KB is the Boltzman constant, and T is the temperature. So this is the expression by which we determine the distribution of the electrons within the volume, right? How these electrons are distributed. At a distribution means at any particular point, whether there is the electron is present at that particular time or not, right? For example, we are talking about this particular volume, right? So we need to determine how many electrons are present in this volume, right? What is the probability of finding the electrons within this volume? Okay, so this is what we mean by distribution of the electrons, right? So at equilibrium, when the system is at equilibrium, then Fe, Fermi-Dirac function, defines the distribution of the electrons. By using this expression, you can define the distribution of the electrons within the volume, right? But what to do at non-equilibrium situations? What to do at non-equilibrium? Okay, there is no expression to find out the probability of the electrons finding in a particular place, finding at a particular time in non-equilibrium situations, right? So Boltzmann transport equation is all about the defining the probability of the electrons at non-equilibrium situation. When the system is out of equilibrium, then Boltzman transport equation is used to define the probability of the electrons, right? Okay, so it means that our further goal is to understand Boltzmann transport equation and to derive Boltzmann transport equation. Okay, so this is our next goal. In short form, Boltzmann transport equation is written as BTE. Okay, so to describe the distribution function in the presence of external field or non-equilibrium situation, we develop the Boltzmann transport equation. When external field is applied, the probability distribution function changes with time. Okay, this Fe, this changes with time when the field is applied. There are basically there are three possibilities, or there are three possible reasons which account for the change in the electron distribution in momentum and position space, right? So there are three basic reasons which account for the probability of the electrons in momentum and position space, right? What are those three reasons? First one is, due to the motion of the electrons, the carriers will be moving in and out of any volume element about the given position space R, right? See, if you have any position momentum space, let's say this is position and this is momentum. Momentum is equal to h cut k, you know that. Okay, so if this is the two-dimensional phase space, x k space इसको बोलते हैं, x k space, right? So see, the electrons are moving in and out of the volumes. Let us assume any small elementary volume here in this xk space, right? So there are situations that some of the electrons are moving in and some of the electrons are moving out of this volume. Okay, so this is the diffusion of the carriers. This is known as the diffusion of the carriers, right? So this is the possibility of change in the probability. Let us denote the probability by F, right? So there may be a situation when n number of electrons are present in this particular volume. There will be a situation when n minus x number of electrons are present in this particular volume, right? So the probability keeps on changing. The number of electrons within this particular volume keeps on changing, right? So this is the probability. This is what we need to find out. We need to find out an expression F for the situation when the probability of the electrons is changing. How the probability of the electrons is changing within this particular volume. कितने number of electron जो है वो change हो रहे हैं इसमें, कितने number of electrons इसमें add on हो रहे हैं, कितने number of electrons इसमें से subtract हो रहे हैं. So that is the thing which we need to find out. Okay. So this is number one reason. So number one reason is due to the diffusion of the electrons. Diffusion of the electrons. This is number one reason. Number two reason is due to the influence of the external forces. Electrons will be changing their momentum, means p value, according to. Okay, so this is the second reason. When external field is applied, let's say when Ex is applied, then the momentum of the electrons changes, right? And due to the change, this change in the momentum is due to the external force. If let's say Fx is the external force applied due to this Ex, right? Then F external is equal to what? Rate of change of momentum with respect to time. Okay, so this will be equal to dp by dt, where p is the momentum. where p is the momentum. Okay, so this is the second reason. Third reason is due to scattering processes, the electrons will move from one momentum space to another due to scattering processes. This makes the equation complicated actually, right? Due to scattering processes, electrons move from one k space to another. So these are three reasons which are accountable for the change in the distribution function of the electrons within a particular space or within a particular volume. Okay, so these three reasons we are going to discuss one by one, right? So firstly, we shall see the impact of first two reasons, and then we will go for the third one, right? These two reasons we are going to derive collectively, and then third one we are going to have a separate discussion and analysis for the third reason. Okay. Any doubt here, students? Any doubt?
No, ma'am.
Yes, students, please do let me know if there is any doubt, because if I will go on speak and you are just going to become listener, then the lecture is not going to be very impactful, right? So if there is any doubt, please keep asking me so that I can resolve your doubts. But otherwise, you have the videos even after the lecture, so you can also listen those lectures. But if you have any doubt, please do ask. Okay. Okay, so let us discuss these three impacts. Let us discuss these three reasons which are accountable for the distribution function and which is accountable for the Boltzman transport equation. Okay, so now let us assume a one-dimensional situation where the momentum of electron is where the movement of the electrons is along x-axis. Okay, so we are taking a situation where the movement of the electrons is along x-axis only, right? And let us assume this situation in a two-dimensional momentum, position, phase space, right? So we are taking a two-dimensional momentum, position, phase space wherein the x-axis is meant for the position space and y-axis, vertical axis, is for the momentum. So here px is equal to h bar k. K is the momentum vector, you know that. Okay, kx, right? So the motion or the movement of the electrons is restricted to x-axis only. We are taking this situation for simplicity. However, by the end we will go for a three-dimensional problem. We will go for a three-dimensional situation, right? So we will consider this situation along x-axis, and then by the end we will generalize the equation for the three-dimensional space. Okay. So it means that at some particular position x, momentum p, and time t, we want to determine the probability fx kxt, that whether this particular state is occupied or not, right? Let us assume this is any point which is defined by the position x, momentum vector kx, and time t. Let us say that at this particular point of the phase space, the probability of finding the electron is f x kx t, is denoted by f x kx t. Okay, so at equilibrium this could be determined by using Fermi-Dirac function. अगर equilibrium होगा system के अंदर, then this f could be determined by simply by using the Fermi-Dirac function जो हमने यहाँ पे लिखा था. Let us say this is equation number 1, right? But we are talking about a situation which is out of equilibrium, right? Means we are talking about the non-equilibrium situation, right? So it is not determined to, it is not possible to determine the value of f using Fermi-Dirac function at non-equilibrium situation. So therefore, our goal is to find out an equation for f, x, kx, and t at non-equilibrium. Okay. Now we know that F external, applied external force, is equal to dp upon dt, rate of change of momentum with respect to time, which is further equal to d by dt, and we know that p is equal to h cut k. Okay, because h cut is h upon 2 pi, you know that, and k is the momentum vector. Okay, which is further equal to minus gradient of electric field, right? This is the expression for the, you know that f is equal to what? Rate of change of E with respect to position. So this is minus gradient of electric field. ये बहुत basic चीज है, +2 में आपने पढ़ा हुआ है. Okay, and this is further equal to minus QE. This is another way of writing force, right? Minus charge on the electron into multiplied by the applied electric field. Okay, so this is in absence of, see, this expression is in absence of the magnetic field. In absence of मैग्नेटिक फील्ड. अगर मैग्नेटिक फील्ड भी होगा तो इसमें दूसरा कंपोनेंट भी ऐड हो जाएगा, राइट? इन दैट केस द फोर्स इज गिवन बाय द नेट फोर्स इज गिवन बाय द लॉरेंज फोर्स. You might remember that. Okay, but in this situation we are assuming that this is just a electric field and the magnetic field is absent over here, right? So let's see, this is equation number 2. Let's say this is equation number 2. So let us integrate this equation. Let us integrate this equation. So let us take this part and this part because they both are equal. So it means that d by dt of h cross k is equal to minus QE, right? When you integrate this, you'll find h cut k, because this is time dependent, and this is equal to h cut k when the field is switched off, when the time is equal to 0, plus integration 0 to t minus QE dt. Okay, so this is, let's say this is equation number 3. Okay, also from the energy momentum space diagram, आप लोगों ने E के diagram पढ़ी हुई है, so I'm not going to talk much about the E के diagram, but you must remember that in E के diagram, K is on the x-axis, E is on the y-axis, and the situation was like this. आपके डायरेक्ट बैंड गैप, इनडायरेक्ट बैंड गैप वहां से आते थे, Okay, so if we talk about the EK diagram, आपने ये band theory of solids में पढ़ा हुआ है, so that's why I will not repeat the things again, right? You must recall, and if you don't remember, you must go to the Kittel, you must take the book of Kittel, and you should see what is there in the band theory of solids and what is EK diagram, right? So if you talk about the EK diagram, the velocity, the time dependent velocity of the electrons is given by using the slope of energy, divided by h cross. So this should be slope in k space E, slope of energy in k space E, okay, divided by h cut. Okay, and this is t dependent, time dependent, so you can say this is et. Okay, so this is equation number let's say 4. Okay, and similarly, if you uh, if you integrate this equation number 4, you can get uh, uh, the position. This is velocity, this is, now you are talking about the position. So position is what? dr upon dt is equal to velocity simply, right? Velocity is time dependent. And then from this equation you can say that if you integrate this equation on both sides, you will get the expression for the position vector. So position vector will be r, time dependent hai, so this is equal to r at t is equal to 0 plus 0 to t v naught t, sorry, you don't need to write v naught here, vt dt. Okay, so this is the position vector, right? So now these are the three equations which are accountable for the behavior of, or which is accountable for the journey of the electron within the phase space, within the two-dimensional phase space, which is momentum space, phase space, right? Using these three equations, you can draw the you can explain the motion of the electrons in the XK diagram. Okay, and the trajectory of an electron motion is represented by just a second. Using these three equations, the trajectory of the electron within the phase space can be defined, and if you plot the trajectory of the electron within the phase space, it looks like this. This is position, this is momentum, P is equal to H cross K, right? So if the electron is coming from outside, let's say from here, then the trajectory of the electron is just like this. Okay, and this is time dependent trajectory. T is equal to, it depends upon xt, it depends upon momentum t. Okay, so this is the trajectory. Okay, I think time is up, right? No. Yes, students, up to when this class is?
10:25.
10:25. Okay, so 5 minutes are there. Okay, so this is the trajectory of the electrons within this momentum space phase diagram, right? Let us say in this trajectory, the position of the electron is represented by this, and this is the probability of finding the electron at this particular position, x, px, t. Okay, So now the probability upstream, that is at a time earlier than t, at a time earlier than t, at a momentum earlier than p, and at a position earlier than x. If we want to find out that probability, that will be somewhere here, right? See, this is the time which is earlier than this time, momentum will be earlier than this, x पोजीशन भी इससे पहले होगा. So this is the situation, or this is the position where the parameters are early than this position, than this particular position. Let's say that at this point the f is represented by f x minus dx, px minus dp, and t minus dt, right? So this point is represented by f x minus dx, px minus dpx, and t minus dt, right? But इसको आप कैसे लिख सकते हो? This could be written as f x minus c. What is dx? Dx upon dt is velocity, right? Dx minus dt is velocity, sorry, dx divided by dt is velocity vx. So it means that vx is equal to dx by dt. Sorry. So it means that here instead of dx we can write it as vx dt. Similarly, px minus dpx, right? So we know that force, external force is equal to dpx upon dt. So it means dpx is equal to force into dt. So this could be written as force, external force into dt, and comma t minus dt, right? So this is how we can represent this point, point which is earlier than the point fxpt. Okay, but the probability of finding the electron on the trajectory is same everywhere, right? The probability here will be same as that of the probability here, right? If for n number of times the electron is present in this particular point, then same number of times there is a probability that the electron will be present on the second point, right? So it means that f x p x t is equal to f x minus vx dt, px minus f external dt, t minus dt. Okay, this will be equal to this. Okay, so both are equal, and we also know that in steady state the movement will be equal, means the electron coming in is equal to the movement coming out. So in that situation the rate of change of the electrons will be equal to 0. So what does it mean? That rate of change of probability is also equal to 0. So df by dt is equal to 0 in steady state. And so therefore for the state f x p x t, if you differentiate, if you take a partial differentiation of this f x p x dt, then we will get df upon dt is equal to, see, there are three variables x, px, and t, right? So this will be df by dt plus df. This is also varying with respect to x, and this is also varying with respect to t. So here dx by dt will also be there, plus df by, this is varying with respect to momentum, so dp x by dt will also be there, and this is equal to 0, right? In steady state, the probability rate of change of probability with respect to time is equal to 0. So we take the differentiation and then it is equal to 0. Okay, so what does it mean? See, what is this? What is dx by dt? What is dx by dt? Anyone? Yes, this is velocity, right? And what is dpx upon dt?
What, ma'am?
What is dpx upon dt? What is rate of change of? Yeah, this is force, right? So हम इसको कैसे लिख सकते हैं? This could be written as df upon dt is equal to df upon dt plus df upon dx, and dx by dt is written by vx, so हम इसको यहाँ पे vx लिख रहे हैं, plus df upon dpx, and this could be written as external force, and external force is in the direction of x, so इसको हम fx लिख सकते हैं. So this is fx, this is equal to 0, right? But as I told you in the beginning, this equation talks about the rate of change of probability of the electrons with respect to time, and this is only in x direction, right? But if we generalize this equation for three-dimensional space, then in 3 dimension this equation could be generalized in 3D. In 3D, the above equation becomes df by dt is equal to df by dt plus velocity in 3 dimensions. So I'm not writing it x, v dot rate. See, this was df by dx, but in 3 dimension we could take it as gradient in space r, where r is the 3-dimensional space, f plus similarly here. So now this is not in x direction, this is in all directions, so it could be written as fe, which means that external force, it may be from any direction, dot gradient of f in p space. Okay, this is equal to 0, where let me explain all the terms over here, where fe is equal to minus QE if it is only electric field, but if it is magnetic field as well, then it could be written as QE minus QV cross B, Lorentz force हम जिसको बोलते हैं, Lorentz force. This will become Lorentz force. Okay. Then del RF is equal to gradient of f in 3-dimensional space, so it could be df.
Excuse me.
Yes बेटा बोलिए.
Time हो गया.
हाँ बस ठीक है, I'm done. So just let me write the terms and then it will be over. Okay, so this is df by dy y cap, and then df by dz yeah, z cap, z direction, right? Similarly, dp df dpf will be equal to del pf will be equal to df upon dpx px cap plus df by dpy py cap plus df by dpz dpz cap, and P is equal to H cross K. Okay, so this is called this equation number